Hello friends, welcome to the course Essentials of Data Science with R Software 2, where we are trying to learn the topics of sampling theory and linear regression analysis. In this lecture, we are going to continue with our module on linear regression analysis, and we are going to learn the topic of simple linear regression analysis with R software. So, you can recall that in the earlier lecture, I had considered the test of hypothesis and confidence interval for the regression coefficients, slope parameter, intercept term, and for the variance sigma square. So, we had seen conceptually and in theory that how these expressions are obtained, and we also constructed the confidence interval for the slope parameter, intercept term, and variance. Now, in this lecture, my objective is that I would try to show you all those things in the R software. So, what I will do? I will try to consider the same example which I had considered earlier on a simple linear regression analysis, and I will try to show you that how you can extract the information on the test of hypothesis and confidence interval under the command LM. You can recall that we have used the command LM linear model to find out the simple linear regression model in the earlier example. So, we will continue with the same example, and I will try to show you that how you can obtain such values. So, let us begin our lecture. Okay, so you can recall that I had earlier considered this example in which we had collected the data on 20 students on their marks obtained and the corresponding values of number of hours of study. So, this marks are indicated by Y, and the number of hours per week of study, they are indicated by X. So, we have got here 20 pairs of observations on Xi and Yi, and then we had entered this data and we had used the command LM Y tilde X to obtain the linear model, the fitted linear model, and then we had earlier also used the command summary on this function. So, and then we had lots of outcome. So, again I am going to use the output of the summary command, and I will show you that the information on test of hypothesis and confidence interval, it is embedded in the outcome of summary command, and how to read it, how to get it, that is my objective to show you here. So, if you remember, if I try to do this execute this summary command on this function LM Y tilde X on the R console, we get this type of outcome. There are many values, and I had promised you that as I am going further into the lectures, I will try to show you the interpretation of all other parts. So, if you remember, we already have done this part. In this part, this was the estimate of intercept term beta 0 hat, or say B0, value of B0, and this was the estimate of slope parameter, say B1, and after this we also consider this part. This was trying to give us the standard error of intercept term, and this 0.4379 was the standard error of B1, and we also had considered his part. So, up to now we have covered this part of this software outcome. Now, we are going to first consider on this part which I am highlighting in color red. Right. So, let me try to show it on this, on the screenshot. So, I am going to first consider here this section which I have denoted by number 3, this section here which I am denoted by number 4, and after that I will try to give you the interpretation of this part which I have denoted at section 5. So, now I will try to take one by one these parts, and I will try to show you. So, now I have taken here this part over here, and I will try to explain you this number 3 and number 4 part on this slide. Right. So, here I am going to consider the test of hypothesis for beta 1 and beta 0. you can recall that when we consider the test of hypothesis, when we have taken for the slope parameter beta 1 was taken as beta 1 0. Now, what are we going? We are going to assume that this beta 1 0 is equal to 0. So, we are essentially going to test H naught beta 1 is equal to 0. And similarly, for the intercept term also, we had considered this H naught beta 0 is equal to beta double naught. So, this beta double naught is going to be considered as 0. So, we are interested in testing the hypothesis H naught beta 0 is equal to or beta naught is equal to 0. The reason that why we are taking 0, because 0 has got some nice interpretation which is useful in the variable selection and in making a decision whether the variable is important in some sense or not. Right, but this I will try to consider later on. At this moment, my objective is to show you that what is happening in the R software. So, whenever you are trying to consider the outcome of any software related to the linear regression analysis, usually they will be giving you the outcome of the null hypothesis where the corresponding parameters are equated to be 0. Right, something like H naught beta 0 equal to 0 sometime and say beta 1 equal to 0. So, we remember that when I want to test the H naught beta 1 equal to 0, then we had considered the test hypothesis to be like this: beta 1 minus this is the value of beta 1 0, which is equal to here 0 divided by standard error, and the outcome of this statistics, which is 7.778, this is shown here. Try to see the movement of my pen. This is here. So, if you try to consider the column number which is named as 3, then this is here the value 7.778, which is the t value, and this t value is corresponding to the slope parameter, right. And similarly, if you try to consider the null hypothesis H naught beta naught equal to 0, then we had seen that the corresponding statistics was given by this, and in the software this outcome is going to be indicated by this value here. Try to see, if you come to here, just try to see the movement of my pen in blue color. Here you have a value 5.927. So, this value here 5.927 is the t value corresponding to the intercept term, that is H naught beta naught equal to 0, and which is the value of this statistic. Right. Okay. So, now you can see here that the column which is called as here t value, that is trying to give you the corresponding t values of different null hypothesis of different regression coefficients. Okay. Now, I try to use a different color pen. You can see here this is my color of pen. So, you can now watch it. So, I come here on column number now 4. You can see here in the column number 4, it is written PR inside parenthesis greater than absolute value of t. So, this is the probability that the t value is greater than absolute value of t. So, this is essentially your p value. So, this value here, which is 1 point, you can see here 1.31, now you can see it clearly here, 1.31 into 10 power of minus 5, this is the here, this is here the p value corresponding to the null hypothesis H naught intercept term, that is beta naught equal to 0. So, this is the p value corresponding to this t naught. And similarly, if I try to take here different color, this second value here 3.65
into 10 to the power of minus 7. This is also here a p value, and this value p value is corresponding to, you can see here, this is corresponding to the regression coefficient associated with x. So, this is the p value corresponding to the null hypothesis H naught beta 1 equal to 0, right. So, this is how you can see that how the things are happening. For example, now you can come here, now you can see here very clearly on this screen that this is the t value and this is here the p value. This is t value and this is here the p value, and you can see here the correspondent with respect to on the left hand side. So, the first row is indicating the intercept term and the second row is indicating for the slope parameter. So, now you can see here that in the first row this is the value of t statistics corresponding to the null hypothesis H naught intercept term equal to 0, and this is the corresponding p value. And similarly, the second row, this is the value of t statistics corresponding to H naught slope parameter equal to 0, and this is here the p value, corresponding p value. So, now you can see here that the obtaining the value of t statistics etc. in software is very simple. The only thing is this, you should know what are these values, how to identify that the corresponding value is for intercept term or for slope parameter. Now, I come to this part number here 5. You can see here it is written here signif.codes codes. So, this is actually significance codes, right. So, this is essentially the value of actually alpha, level of significance, right. So, you can see here this is taking so I can write down here this is actually alpha. So, alpha is equal to 0, alpha is equal to 0.001, alpha is equal to 0.01, alpha is equal to 0.05 and so on. So, and alpha is equal to 0.1. So, and these stars are indicating the corresponding values over here, you can see here, right. So, that is essentially trying to tell you that if you try to look at this outcome, here you are looking, I will try to make it in the blue color, you can see here this for 3 stars. So, 3 stars are indicating that the level of significance what is being used here, this is the corresponding to the alpha where the indication is by 3 stars. So, this is right. So, actually, so alpha equal to 0 is indicated by 3 star, alpha equal to 0.001 is indicated by 2 stars, and alpha equal to 0.01 is indicated by single star, and alpha is equal to 0.05 is indicated by just here dot and so on, right. So, this is how it is trying to indicate that what is the level of significance, what is being used, and then the value of alpha is being used in the test of hypothesis, which has been used by the p value, right. So, this stars are simply indicating the level of significance what is being used, right. So, for example, in this case you can see here I have written here very clearly that if alpha is equal to 0.05, then if you want to test the hypothesis H naught beta 1 equal to 0, then p value is here 1.31 into 10 power of minus 5, which is actually given here, you can see here, right, and which is smaller than alpha. So, I have to take a call. So, the rule was reject H naught when p value is less than alpha. So, I can say here that H naught beta 1 equal to 0 is rejected, right, at alpha level of significance. Similarly, for the intercept term also, the corresponding p value is 3.65 into 10 power of minus 0.7, which is again less than alpha. So, I can conclude here that the null hypothesis H naught beta naught equal to 0 is also rejected at alpha equal to 5% level of significance. And you can also see here that that they have got the interpretation also. You are trying to test, for example, let me try to explain you. You are trying to test H naught beta 1 is equal to 0. What is your here beta 1? Beta 1 is the rate of change in the value of y with respect to x, right. So, you are trying to find out here the rate of change in the marks with respect to number of hours of study, right. So, now looking at the conclusion that H naught beta 1 equal to 0 is rejected, this is indicating that beta 1 is not equal to 0. Beta 1 is not equal to 0, that means the corresponding value of here x is an important variable, and it is affecting the outcome, and that is obvious that the marks of the students are going to be affected by the number of hours of studies, and this test of hypothesis is also indicating the same conclusion, that the variable which you have considered as the number of marks obtained, the number of marks, they are depending on the number of hours of study, and hence the variable x, which is the number of hours of study, is an important variable that is affecting the outcome. Means how to understand it, how to show it. So, let me try to take here the opposite story, and I try to write down in a blue color so that you can identify it. Our model was y is equal to beta 0 plus beta 1 x plus epsilon. Now, you try to test the hypothesis H naught beta 1 is equal to 0, and suppose it is accepted, H naught is accepted. That means beta 1 is equal to 0 in the population. That means my model will be revised as beta 0 plus beta 1 equal to 0 times x plus epsilon, which is equal to beta 0 plus now 0 into x plus epsilon, which is beta 0 plus epsilon. So, now you can see here that in this model there is no role of x, and also if you try to see, if you are trying to accept the hypothesis that H naught beta 1 is equal to 0, so beta 1 is trying to measure the rate of change in the marks with respect to the number of hours of study. So, you are saying that beta 1 is equal to 0, that means practically there is no change in the marks of the student when the number of hours of study changes. So, that means the marks are independent of the number of hours of study. So, whether the students studies or not, the marks are not going to be affected. Well, we all know that this is a wrong conclusion. This should not happen, and that is what exactly your test of hypothesis is indicating here when you say that H naught beta 1 equal to 0 is rejected. That is what you want, right. Okay. Similarly, now if I come to the interpretation of say H naught beta naught equal to 0, then this is also getting rejected. That means the intercept term is playing an important role in the model, and it is not equal to 0, right. So, that means we have to consider, and it is correct, and if you go logically also, that is also correct. If a student is not studying at all, but suppose the student is attending classes, he is doing assignment, etc., then yes, surely he will get some marks in the exam. That cannot be equal to 0. I mean, that we know from our experience. So, whatever are the conclusions which we have obtained on the basis of test of hypothesis, they are also getting confirmed with what is happening in the real life, in the real experiment. So, now you can see here that the model which you had obtained, that has also been verified through the test of hypothesis, and you can believe that up to now the model is doing well. Okay. Now, if you want to find out the confidence interval, for that we have a command here conf int, that is the short form of confidence interval, CONFINT. This is actually used to compute the confidence interval for one or more parameters in a fitted model. And this is actually command has to be used along with actually the command LM. Whatever is the output of the LM, this conf int command will extract the confidence interval from the outcome of LM, right. So, the command here is you try to write conf int, then inside the parenthesis you try to write down the object, that means the outcome of the LM command, and then you try to give here parameters and the label. One thing what you have to keep in mind here that there are some different interpretations here which you have to keep in mind. Means obviously, when I say object, this is a fitted model, means I will try to show you with the example also, and when I am trying to say here PARM, this is indicating the parameters. So, we would like to tell the software whether we want the confidence interval for intercept term or slope parameter, and in multiple linear regression model, when we have more than one regression coefficient, that what are the parameters of which we want to have the confidence interval, right. And if you do not write anything against this PARM, then all the parameters whatever are involved, they will be considered and you will get the confidence interval for all the case. For example, in the simple linear regression model, if you do not use PARM, then you will get the confidence interval for slope parameter as well as for the intercept term. And then there is a option here level, LEVEL. This is indicating the confidence level. Remember one thing, if alpha is the level of significance, then 1 minus alpha is the confidence level. So, in this function the input has to be given in terms of confidence coefficient. So, that is the value of 1 minus alpha or 1 minus level of significance. So, now first I try to show you the outcome on this screen and then I will try to show you on the R console. So, if you remember, we had used this command LM inside parenthesis y tilde x. So, this will give us the fitted linear model. Now, I am not using here PARM command or option because I want the confidence interval for both the parameters. Remember, confidence interval is obtained only for the regression parameter, not for the sigma square. For sigma square, we have to do it separately. So, at this moment with this conf int command, I am going to consider the confidence interval only for the regression parameters. So, I am trying to fix here level is equal to 0.95, that means my alpha is 0.05. So, the confidence coefficient is 1 minus alpha, which is 95%. Now, if you try to see the outcome, it will look like this. So, you can see here first row here is 2.5%, then 97.5%, and then in the first column there is intercept term, then x, then in the second column we have some values like this. So, let us try to consider one by one all the things. So, first I try to consider the second row, which is here, right. So, you can see here there are here two values, one is this and second is this, right. Now, this is trying to give you the confidence interval for intercept term. So, now if you try to look in the bottom of the slide, from the theory we had obtained the 101 minus alpha, which is 0.05, which is 95% confidence interval for the intercept term beta 0 by these two commands, right. And the values which are obtained here, or I say if you try to compute this quantity manually, then you will get the value 48.91 and so on. Similarly, if you try to compute the second value here, the upper confidence limit, you will get the value here 102.64 and so on. And now if you try to see these values in the software outcome, you can see here that this value is given here and this second value it is given here, right. So, you can see here that these values 48.91 and 102.64 and so on, they are the confidence interval for the intercept term, right. And similarly, if you come to the third row, which is here like this is the confidence interval for the slope parameter beta 1. And if you remember, we had obtained the 101 minus alpha percent, or here alpha is equal to 0.05. So, 95% confidence interval for the slope parameter beta 1 as like this. The lower limit was this and upper limit was this. So, if you try to compute it manually on the basis of given set of data, you will get here this value 2.48 for the lower confidence interval and the upper confidence interval to be 4.32 and so on. And this is the same outcome which is given here. So, you can see here this is how you will obtain the values of the confidence limits, and so you can obtain the confidence interval for all the parameters. And if you try to give here use the option here PARM parameter, then you can specify what you want. If you want the confidence interval only for intercept term or only for slope parameter or some collected slope parameters, then you will get only that outcome, right. So, this is about identifying the confidence interval from the outcome of R software. Now, I consider the test of hypothesis for the sigma square, but before that I can show you all these things on the R console. Okay, so I try to copy this command so that I can save my time. Okay, and yeah, I already have entered these values of x and y. So, you can see here y is here, x are like this, and if you try to use here the command y lm command y tilde x, this will come like this, and if you try to use the summary command on this lm y tilde x, it will come out to be like this, right. So, it is not giving you the confidence interval, but now if you try to the same command which I used here, then you can see here this is the same outcome which you have obtained here, right. So, you can see that it is not difficult, right. And if you want to look at this t values, you can see here where I am highlighting, right. This is the t value corresponding to intercept term, this is the t value corresponding to beta 1, this is the p value corresponding to the intercept term, and this is the p value corresponding to the slope parameter. And remember, this is for h naught when the given value is assumed to be 0, right. Okay, so now you have seen these things. So, now let me come back to the confidence interval for sigma square. So, first we assume here that y1, y2, yn, they are independently distributed observation from a normal distribution, because for the validity of chi-square you need the observation from normal distribution. And you can recall that we had earlier discussed that the test statistic for sigma square was found using the result summation yi minus y bar whole square divided by sigma square, which follows a chi-square distribution. And actually this is a very general test of what I am going to show you here. Why I am calling it general? You will see that many more things can also be found from the same test. In the context of linear regression model, what we are considering here, we have this model. So, your yi's are obtained or they are assumed to follow this model, right. And you can see here that yi depends upon two parameters, beta 0 and beta 1. Means unless and until you know beta 0 and beta 1, you cannot move further. In the sense, for example, if you want to find out sum of square due to residuals, this was defined as summation ei square, which was summation yi minus b0 minus b1 xi whole square. So, unless and until you know the values of beta 0 and beta 1, you cannot obtain the sum of square due to residual. So, it depends on two parameters, and that is the reason that here the degrees of freedom are n minus 2. So, this 2 is actually indicating that in order to know this quantity, you should know two values. So, the degrees of freedom are reduced from n to n minus 2. Well, the concept of degrees of freedom has several definitions, and different topics can give a different interpretation, but well, I just told you so that you do not get confused, because you will see that this degrees of freedom will be getting changing when I come to the multiple linear regression model, and there I will try to give you a more formal procedure that how we are determining this degrees of freedom. You had seen earlier that the test statistics for testing S naught sigma square equal to sigma naught square was given by this chi-square C, which follows a chi-square distribution with n minus 1 degrees of freedom under H naught. So, now in this case the rule is the same, that we are going to reject H naught against H1, which is a two-sided hypothesis at alpha level of significance if p value is smaller than alpha. What you have to keep in mind that the package which we are, or the command which we are going to use to obtain the confidence interval and test of hypothesis for sigma square, that requires to express the H naught in a different way. We have done in the theory that it is our null hypothesis is H naught sigma square is equal to sigma naught square. This thing can also be written as sigma square upon sigma naught square is equal to 1, right. So, this software requires that it is trying to replace this 1 by some value. That can be 1, that can be 2. For example, if I say if sigma square equal to sigma naught square is equal to 2, so that means it is going to test the hypothesis that H naught sigma square is equal to twice of sigma naught square. So, when you want to test the equality of sigma square and sigma naught square, then in the software you have to provide the value as 1, right, which is the ratio of sigma square and the given value of sigma square as sigma naught square, right. And you can recall that we had obtained the confidence interval also in the case of sigma square using this statistics, and based on that we had obtained the confidence interval like this. So, this is a quick revision for you, right. Now, I am going to use my software. So, in order to do the inferences for sigma square to test the hypothesis and for confidence interval, we need to install a package whose name is ENVSTATS. You have to keep a note that here this E and this S, they are in capital letters, right. So, you need to install this package and then you have to load this package, and then the command here is var test, VARTEST, but again you have to be careful that here this capital T is used. So, in the test the first T is in capital letter, and then you have to first give the observations on which you want to conduct this hypothesis, and then you have to choose the option alternative is equal to within double quotes 2 dot sided. So, that will indicate that your hypothesis is of type not equal to, otherwise there are other options, but our interest here is in 2 sided. And again you have to give the confidence level, which is the value of here 1 minus level of significance, which is alpha, right. And once now you are trying to say here this sigma squared is equal to this one is actually the value of sigma square upon sigma 0 or sigma naught square. So, this is the ratio which you have to be careful, right, and then you have to give the data name, which we are not using because we are supplying, otherwise you can give it. So, that is what I am trying to explain here. X is the numeric vector, alternative is the character which is trying to indicate whether your alternative hypothesis is 2 sided or type of greater than or less than, right. And similarly, this confidence level is the value between 0 and 1, which is equal to 1 minus alpha, 1 minus level of significance, and sigma dot squared is the numeric scalar indicating the hypothetical value of the variance, okay. And data dot name, this is the character string indicating the name of the data to be used for the test of variance. So, now we already have the data on the marks of the student, which we had stored here as a y. So, I will try to use this command var capital T E and then small letter est, this data on y, and my alternative here is 2 sided. So, you can see here my null hypothesis is now reframed as h naught sigma square is equal to 1. Okay. So, confidence level now here is 0.95 and sigma squared sigma dot squared equal to 1, and if you try to see, this is the outcome that you will get. So, here it is the first line is trying to give you that what is your null hypothesis, that means variance is equal to 1. Then it is trying to give you the alternative hypothesis, which is not equal to 1. Then it is trying to give you what is the name of the test, this is the chi-square test on variance, because there are different types of chi-square test. Okay. And what is here estimated parameter, it is trying to estimate the variance, right, on the basis of given set of data. Then what is the data which you have used here, this is y, what is the test statistics, this is chi-squared and its value is coming out to be 272.95.2, right. And what are the corresponding degrees of freedom, the degrees of freedom were n minus 1, n is 20, so this is 19, and p value which you have which you would like to know, it is 0. So, once again you can see here that this that you have to compare the p value with the value of alpha, and you have to take an appropriate decision. And then the 95% confidence interval is given by here like this. So, the lower confidence limit is 830.8453 and the upper confidence limit, this is UCL, this is 3064.6325. Right. So, and then here is the screenshot of the same thing what I have shown you here, and now based on that you can take a conclusion. How? This chi-square C value, this is coming out to be 272.95.2, which is here you can see here this value, right. And then we have here lower confidence limit, upper confidence limit, which are coming out to be here like this, which are indicated here, right. So, based on that you can take a conclusion, since p value is equal to 0, which is smaller than alpha. So, your h naught sigma square equal to 1 is rejected, right. So, this will give you an idea about the variability. Now, let me come to the R console and try to show you it on the. So, you can see here my y that I already had entered is given like this, and my this package environment stats that is already on my computer. So, I am just uploading it, and then I am using the command here for the variance test. You can see here this is now here the outcome. So, you can see here that this is here your 95% confidence interval, and sample estimates are here given to be here like this. Well, you can see here there is some difference in the structure of outcome, that is because of the different versions of R. but the outcome is the same. So, this is giving you value of here the sample estimates of variance, and this is here the confidence interval. And this is here, you can see here the p value is here given to be like this, right. And yeah, the value of chi-square statistics is coming out to be here like this, right. So, you can see here that it is not really actually difficult to get it done, right. Okay. So, now let me finish this lecture. So, now we have learnt how to obtain the point estimates of regression parameter as well as variance sigma square, how to obtain the confidence interval, and how to conduct the test of hypothesis for the regression coefficient as well as for the sigma square. We also have now understood how to obtain the fitted model, fitted value, residuals and those things. So, now I will stop with the chapter on simple linear regression modeling with the brief description of these concepts. Well, these concepts are brief, but they are very important. Their real use will come when we try to use them in the next chapter on multiple linear regression model. So, my advice to all of you will be that you try to take any data set from the book, from the chapter of simple linear regression model. Just take a small data set that you can enter from your hands and you can see what is happening. You try to make plots, try to estimate them, try to obtain confidence interval, try to conduct test of hypothesis and see what you were thinking, is that really happening? And more you practice, you will have a more understanding of the process and the data, that how looking at the values of the software outcome you can make a correct interpretation, which is the soul of statistics. It is just like by looking at an X-ray or say MRI report or ECG report, the doctors, different doctors can make different types of conclusion. And we always say that the doctors learn by their experience, and a doctor is a better if he is more experienced. So, more they practice, they become a better doctor. Same is with you also now. More you practice with these data sets, they will give you insight into the data, what is happening. As we said that the data is deaf and dumb. Data cannot raise the hand and can tell you, okay, I have this information, I have this type of model, but this is the tool by which you can extract the information. Now you know, data had never told you that what is the relationship between x and y, but now you know what is the relationship and what are the different type of information which is contained inside the data, which has been obtained not by looking at the horoscope or the lines of the hands, but they are based on pure statistical tool. And now I do not need to explain you the importance of statistical modeling in data sciences. Everybody knows. So, these small things, small concepts will help you in taking bigger decisions. So, you practice, and I will see you in the next lecture with a new topic on multiple linear regression model. Till then, goodbye.